Hi everybody. So chapter 12 is on inference on categorical data. So this is data that is arranged into categories. And in section 12.1 we'll talk about the goodness of fit test. So we'll only have one objective in this section, form a goodness of fit test. Couple things about, just to remind you about, in this section we'll be using the chi-squared distribution for the goodness of fit test. A couple things to remind you about the chi-squared distribution is that it is not symmetric. Its shape, again, depends on the degrees of freedom. And as the number of degrees increases, it becomes more nearly symmetric or more normal. Remember, the values of chi-squared are never negative. So they either have to be greater than or equal to 0. And then just remember that this is how the shape changes as the degrees of freedom increases. So just to remind you about the chi-squared distribution before we talk about the goodness of fit test. So the goodness of fit test is an inferential procedure used to determine whether a frequency distribution follows or is similar to another specific distribution. So let's look at, so basically we'll have sort of some expected values that we will sort of expect the result to have, and then we'll have some actual observed values, and we're going to compare the expected values to the observed values. Suppose there are n independent trials in an experiment with k greater than or equal to 3, so k has to be greater than or equal to 3. Mutually exclusive outcomes, so again there can't be any overlaps between the outcomes, and let p sub 1 represent the probability of observing the outcome, and e sub 1 represent the expected count of the first outcome, p sub 2 represent the probability of the second outcome, and e sub 2 represent the expected count of the second outcome, etc. Right? So the following expected counts for each possible outcome are given by the following equations. So right, you just take the number times the probability in each case. So let's look at an example. So let's say that a sociologist wishes to determine whether the distribution for the number of years of caregiving grandparents were responsible for their grandchildren is different today than it was in 2000. So according to the Census Bureau, in 2000, 22.8% of grandparents have been responsible for their grandchildren less than 1 year, and 23.9% of grandparents have been responsible for their grandchildren for 1 or 2 years. 17.6% of grandparents have been responsible for their grandchildren for 3 to 4 years, and 35.7% of grandparents have been responsible for their grandchildren for 5 or more years. If the sociologist randomly selects 1,000 caregiving grandparents, compute the expected number within each category, assuming the distribution has not changed from 2000. So what we're trying to sort of compare is whether the distribution of caregiving grandparents has changed from 2000, whether the percentage or the proportions caring for their grandchildren for their certain number of years has changed. So these are the different probabilities then, right? So the probabilities are the relative frequencies from the 2000 distribution. So the probability that the grandparents care for their grandchildren for less than 1 year is this number, from 3 to 4 years is this number, from 1 to 2 years is this number, and the probability that they would care for their grandchildren for 5 or more years is this number. So then the expected value then would just be the number in the sample times the probability. So this is what you would sort of expect the numbers to be if you were to measure them. Now that may not be actually the case when you actually observe things. So let's look at the goodness of the test statistic for the goodness of fit test, and then we'll come back to this example. So the test statistic for the goodness of fit test is given by this formula, so remember sigma just means you're adding. So you're taking the difference between the values you expect to have and subtracting those from the observed values that you're actually observing, and then you square those and then divide by the expected value, and then you add all those values together. And this approximately follows the chi-squared distribution with k minus 1 degrees of freedom, provided that the following two conditions are met, right? All expected frequencies are greater than or equal to 1, right? That is, i.e. is always greater than or equal to 1, and no more than 20% of the expected frequencies are less than 5. Okay, so again, in most cases, these two conditions will be met, so you won't really have to worry about those. But if you're following the procedure in the book that's on the bottom of page 590 and the top of page 591 in that sort of bluish purple box there, this is basically sort of step 3, so we're kind of walking through that procedure. Word of caution here is that the goodness of fit tests are used to test hypotheses regarding the distribution of a variable based on a single population. If you wish to compare two or more populations, you must use the test for homogeneity presented in section 12.2. So the goodness of fit test then, the step 1 then is to determine the null and alternative hypothesis, and that this will always be the same. You don't really have to worry about this, but either the random variable follows the expected distribution, or the random variable does not follow the distribution. So again, the alpha level will typically be given to you. Again, unless otherwise stated, you can assume that the alpha level is 0.05. And then calculate the expected counts, that is, calculate the EIs. Some of these might be given to you, otherwise you would just take the number of things in your sample times the probability of each one of those events happening. And remember that these events, these categories should not overlap. And then, like I said, technically you should verify the requirements for the goodness of fit test, but in most cases they should be satisfied. If the requirements in step 3 are not satisfied, one option is to combine two or more of the low frequency categories into a single category, by the way, so I think in most cases you won't have to do that. Step 3 is compute the test statistic, which again is just the difference between the observed and expected values squared divided by the expected values, and then adding all those up. And then again you can either use the classical approach or the p-value approach. So determine the critical value determined by alpha. Compare that to your calculated value in step 3. And then again, if the calculated value is greater than the value you basically look up in the table, you would reject the null hypothesis. And then if you'd rather use the p-value approach, again, you can use table 7 to obtain the approximate p-value, or you can use some sort of technology to calculate the exact p-value if you want to or if you need to. And then again, just as before, if the probability value is less than alpha, you reject the null hypothesis. And then again, don't forget to state your conclusion in words so that other people can understand what you're saying. Okay, so those are the steps, again, that are sort of outlined on the bottom of page 590 and the top of 591 if you want sort of a place where those are all sort of listed together. So let's go back to that example of caregiving grandparents here, and let's try to calculate this. So we calculated the expected frequencies before. Now let's look at some observed frequencies. So in this case, the sociologist randomly selects 1,000 caregiving grandparents and obtains the following frequency distribution. So then what we'll have to do is compare this to the expected values that we looked at before, and we're going to do this at the 0.05 level of significance. So these are the hypotheses, right? Either the distribution is basically the same today as it was in 2000, or there has been a change in the distribution, how the distribution of grandparents has changed from what it was in 2000. So again, these were the expected values that we calculated before, and these are the observed counts. So you basically want to take the difference between these two, square them, and then divide by the expected counts, and then just add them together. So again, we'll just take the difference between the observed and expected counts for each one, square each one of those values, and then again divide by the expected value. And then finally, the sigma just means we're going to add them together. So that gives us a test statistic for the chi-squared of 6.605. And then again, at this point, we can either choose to use the p-value approach or the classical approach. So the classical approach, we'd want to look up the chi-squared value for 0.05, since that was our level of significance. And since our calculated statistic does not fall within the region of significance here, right, we do not reject the null hypothesis. And then again, using the p-value approach, the p-value is approximately 0.09, which is less than our alpha, which is not less than our alpha value, so we would fail to reject the null hypothesis in that case. So step 5, then we want to state the conclusion, and the conclusion is that there is not sufficient evidence to conclude that the distribution for the number of years of caregiving grandparents who are responsible for their grandchildren is different today than it was in 2000. And again, I guess you should, just to be extra clear, you should state the level of significance there, right? At the 0.05 level of significance. But if you don't do that, I'm not going to take points off. But I might take a couple points off if you just state the conclusion. Whether you accept or reject the null hypothesis, but you don't write this statement down. So this, again, just to remind everybody, this is an important step. So make sure that you write this down or something similar to it. So if you guys have questions about that or anything, let me know. Or anything else, let me know about that too. All right. Hope this helps. In the next section, I guess we'll look at section 12.2, which is tests for independence and homogeneity of proportions.